Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 6, Algebra of Points and One-Dimensional Coordinate Systems. Section 56, the Cross Ratio. We have seen in the preceding section that it is possible to associate a number with every throw of 4 points on a line. By duality, all developments of this section apply also to the other one-dimensional primitive forms, i.e. the pencil of lines and the pencil of planes. With every throw of 4 elements of any one-dimensional primitive form, there may be associated a definite number, which must be the same for every throw projective with the first, and is therefore an invariant under any projective transformation, i.e. a property of the throw that is not changed when the throw is replaced by any projective throw. This number is called the cross ratio of the throw. It is also called the double ratio or the anharmonic ratio. The reason for these names will appear presently. In general, 4 given points give rise to 6 different cross ratios. For the 24 possible permutations of the letters of the symbol T of AB, CD fall into sets of 4 which, by virtue of Theorem 2, Chapter 3, have the same cross ratios. In the array below, the permutations in any line are projective with each other, 2 permutations of the different lines being in general not projective. Row 1, AB, CD, BA, DC, DC, BA, CD, AB. Row 2, AB, DC, BA, CD, CD, BA, DC, AB. Row 3, AC, BD, CA, DB, DB, CA, BD, AC. Row 4, AC, DB, CA, BD, BD, CA, DB, AC. Row 5, AD, BC, DA, CB, CB, DA, BC, AD. Row 6, AD, CB, DA, BC, BC, DA, CB, AD. If, however, the 4 points form a harmonic set H of AB, CD, the throws T of AB, CD, and T of AB, DC are projective, Theorem 5, Corollary 2 of Chapter 4. In this case, the permutations of the first 2 rows of the array just given are all projective, and hence have the same cross ratio. The 4 elements of a harmonic set therefore give rise to only 3 cross ratios. The values of these cross ratios are readily seen to be -1, 1/2, 2, respectively. For the construction of our number system, give at once h of p infinity p0, p1, p minus 1, h of p infinity p1/2, p0, p1, and h of p infinity p1, p0, p2. We now proceed to develop an analytic expression for the cross ratio R of x1, x2, x3, x4 of any 4 points on a line, or in general of any 4 elements of any one-dimensional primitive form, whose coordinates in a given scale are given. It seems desirable to precede this derivation by an explicit definition of this cross ratio, which is independent of von Stout's algebra of throws. Definition: the cross ratio R of x1, x2, x3, x4 of the elements x1, x2, x3, x4 of any one-dimensional form is, if x1, x2, x3 are distinct, the coordinate lambda of the element of the form into which x4 is transformed by the projectivity which transforms x1, x2, x3 into infinity, 0, 1, respectively, i.e. the number lambda defined by the projectivity x1, x2, x3, x4 projective with infinity, 0, 1 lambda. If 2 of the elements x1, x2, x3 coincide, and x4 is distinct from all of them, we define R of x1, x2, x3, x4 as that one of R of x2, x1, comma, x4, x3, R of x3, x4, comma, x1, x2, R of x4, x3, comma, x2, x1, for which the first three elements are distinct. Theorem 13. The cross ratio R of x1, x2, comma, x3, x4 of the four elements whose coordinates are respectively x1, x2, x3, x4 is given by the relation lambda is equal to the cross ratio of x1, x2, comma, x3, x4 is equal to the quantity x1 minus x3 divided by the quantity x1 minus x4 to the quantity x2 minus x3 divided by the quantity x2 minus x4. Assumptions A, E, and P. Proof: the transformation x prime is equal to the quantity x1 minus x3 divided by the quantity x1 minus x divided by the quantity x2 minus x3 divided by the quantity x2 minus x is evidently a projectivity, since it is reducible to a form of a linear fractional transformation, namely x prime is equal to minus the quantity x1 minus x3 times x plus x2 times the quantity x1 minus x3, all divided by minus the quantity x2 minus x3 times x plus x1 times the quantity x2 minus x3, in which the determinant, the quantity x1 minus x3 times the quantity x2 minus x3 times the quantity x2 minus x1 is not zero, provided the points x1, x2, x3 are all distinct. This projectivity transforms x1, x2, x3 into infinity, 0, and 1, respectively. By definition, therefore, this projectivity transforms x4 into the point whose coordinates is the cross ratio in question, i.e. into the expression given in the theorem. If x1, x2, x3 are not all distinct, replace the symbol R of x1, x2, comma, x3, x4 by one of its equal cross ratios, R of x2, x1, comma, x4, x3, etc. One of these must have the first three elements of the symbol distinct, since in a cross ratio of 4 points, at least 3 must be distinct by definition. Corollary 1. We have, in particular, R of x1, x2, comma, x3, x1 is equal to infinity. R of x1, x2, comma, x3, x2 is equal to 0. And R of x1, x2, comma, x3, x3 is equal to 1. If x1, x2, x3 are any three distinct elements of the form. Assumptions A and E. Corollary 2. The cross ratio of a harmonic set H of x1, x2, comma, x3, x4 is R of x1, x2, comma, x3, x4 equal to minus 1. For we have H of infinity, 0, comma, 1, minus 1. Assumptions A, E, and P. Corollary 3. If R of x1, x2, comma, x3, x4 is equal to lambda, the other 5 cross ratios of the throws composed of the 4 elements x1, x2, x3, x4 are R of x1, x2, comma, x4, x3 is equal to 1 divided by lambda. R of x1, x3, comma, x2, x4 is equal to 1 minus lambda. R of x1, x3, comma, x4, x2 is equal to 1 divided by the quantity 1 minus lambda. R of x1, x4, comma, x2, x3 is equal to the quantity lambda minus 1 divided by lambda. R of x1, x4, comma, x3, x2 is equal to lambda divided by the quantity lambda minus 1. Assumptions A, E, and P. The proof is left as an exercise. Corollary 4. If x1, x2, x3 form a harmonic set H of x1, x2, comma, x3, x4, we have 2 divided by the quantity x2 minus x1 is equal to 1 divided by the quantity x3 minus x1 plus 1 divided by the quantity x4 minus x1. Assumptions A, E, and P. The proof is left as an exercise. Corollary 5. If A, B, C are any three distinct elements of a one-dimensional primitive form, and A prime, B prime, C prime are any three other distinct elements of the same form, then the correspondence established by the relation R of AB, Cx is equal to R of A prime, B prime, C prime, X prime is projective. Assumptions A, E, and P. Proof. Analytically, this relation gives the quantity A minus C divided by the quantity A minus X times the quantity B minus X divided by the quantity B minus C is equal to the quantity A prime minus C prime divided by the quantity A prime minus X prime times the quantity B prime minus X prime divided by the quantity B prime minus C prime, which, when expanded, evidently leads to a bilinear equation in the variables x prime, which defines a projective correspondence by Theorem 11, Corollary 3, that the cross ratio, the quantity x1 minus x3 divided by the quantity x1 minus x4 divided by the quantity x2 minus x3 divided by the quantity x2 minus x4 is invariant under any projective transformation may also be verified directly by observing that each of the three types, 1, 2, 3, of projectivities on pages 152 and 153 leave it invariant. That every projectivity leaves it invariant then follows from Theorem 11.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.